Hello, today I'm going to do a problem that involves two objects. It's a kinematics problem, a motion problem, two objects, but it's a little more complex. It's not quite a two-phase problem, but it's going to take us a couple steps. So that's what I'm going to work on. The problem reads, a stone is dropped from rest from the top of a cliff that is 24 meters high. From ground level, a second stone is thrown straight upward at the same moment the first stone is dropped. The initial speed of the second stone is exactly the same as the speed that the first stone hits the ground with. How far below the top of the cliff do the stones meet? So this is a complex problem. Our problem-solving strategy is what we start with. So even if you have no idea where to start with a strategy, which involves drawing a picture. So we have a cliff, the ground, and a stone is dropped from rest at the top of a cliff that is 24 meters high. Okay, 24 meters high. And a second stone is thrown straight upward from ground at exactly the same moment. And we know that the initial speed of this second one equals the final speed of that one. All right. How far below the top of the cliff do they meet? So at some point, they're going to be at the same height. So where is that point? That's what we're looking for. So there's my basic picture. And then with the picture, include your origin and your coordinate system. So I'm going to use my standard coordinate system, up and right positive. Oops, that's a Y. And my origin, I like picking the ground as my origin. So I'm going to set my ground to be x equals 0. Okay, so there's my first step. I've got my picture, I've got my origin, I've got my axes. Now I need to do my knowns and my unknowns. So this is our chart of the 6 variables. So x1, x final, v initial, v final, a, and t. But I got two objects, I got to do it twice. I think I'll do it in a different color. Let's see. So for object 2, I'm going to make this one green. There. So object 2, we've got the same 6 variables. V initial, V final, A, and T. Okay, so what can we fill in? What do we know? What are knowns? What's our unknown? And are there any assumptions we can make to fill in? And sometimes there'll be blanks. And blanks in our chart, just fine. So for the one that's dropped at the top, well, it starts at 24 meters above, and it's going to fall. Now you might want to say that x final is 0. That it ends on the ground. And it does end on the ground, but that's not the time we're interested in. We care about the time from dropping to meeting the other stone. So, all right, we don't know. That's kind of what we're looking for, x final. V initial, it's dropped, so that means it doesn't have any initial velocity. V final, how fast is it going when they meet? Don't know. What's the acceleration? Well, it's in free fall. It's not hitting not touching anything, not interacting with anything but gravity. So we've got a negative 9.8 there. And we don't know anything about time. Now stone 2, x initial, starts at the ground. X final, well, that's where it meets. That's what we want to know. It has some V initial. We don't know what it is. At V final, how fast is it going at that point? Don't know. Acceleration, gravity, negative 9.8. And again, we don't know how much time it takes to go from here to here. So I look at this and I say, is there enough information for me to solve the question right now? Can I solve for x final in either one of these? Look at my 3 equations. Well, x final equals x initial plus v initial t. Okay, need to know t. V final equals V initial plus AT, no. V final squared equals V initial squared plus 2A delta X. Still need to know V final. Nothing helps, and this I have even fewer, so definitely not going to be able to do it here. So what do? Well, I do have one more piece of information. I know that the initial velocity of this stone being thrown upward is the same as the velocity that this stone hits the ground with. So if I can figure that out, I would be able to put it in right here. So let's see if we can figure out what that initial velocity is. We do know this. Well, we can figure it out. So let's figure it out. How fast does the first stone hit with? All right, so I'm going to do a new chart because this is for stone, let's call it A. I'll call this one A. So for stone A, this is from being dropped until it's about to hit the ground. So for that, what do I have? X initial, V initial, V final, A, T. Okay, so here's what we can fill in this case. Starts 24 meters up, ends at the ground in this case. It's dropped. We don't know how fast it hits the ground with. That's what we're trying to find. We don't know how much time it takes. All right. So we don't know time, and we want to know V final. If we don't know time, there's one equation that we can try to use, and it's the squared equation. V final squared equals V initial squared plus 2A delta X. That is 0. I'm looking for V final. I know 2, I know my acceleration, and I can figure out my change in X. This will work. This will tell me what V final is. So V final squared equals 2 times my acceleration. Ooh, I'm worried about that because I'm going to have to take a square root, and I can't take a square root of a negative. Okay. What's my change in X? And remember, delta X is X final minus X initial. X final is 0 minus X initial. Ah, there we go. Negative 24. It drops 24. So that gets rid of that negative. Okay, so V final squared. So V final is going to be the square root of, well, I don't know what. I didn't write that down. What we get is, is going to be plus or minus 21.7 meters per second. Why plus or minus? Because I took a square root. This means that I need to choose which of the two roots, plus or minus, is appropriate in this case. Look back to the physical situation. So in this case, the final is right before it's going to hit the ground. Is it going up or down at that point? Down. So we should choose the positive root. So my V final is a negative 21.7. That's how fast the first stone would hit the ground with, which means that's how fast the second stone is thrown up with, up. So this becomes a positive 21.7. And if you put a negative in there, it's on the ground and it's being thrown downwards. Wouldn't make sense. So there we go. We have our plus 21.7. Now do I have enough information on the green one, on number, or letter B, stone B, to figure out where they meet? Again, I don't know time. I don't know V final. Well, how am I going to do this? Okay, here's where the cool thing about two-object problems comes into play. We have two pieces of information that are not quite visible there. We know that X final of stone A is equal to X final of stone B. We know that our X final position, our final position, is the same for both of them. We also know that the time for A and the time for B are the same. So if the times are the same and the final positions are the same, what can we do with that? Well, let's figure out an equation for X final of stone A. Let's figure out an equation for X final B. Set them equal to each other. I'm going to use the big one for both of these because X final equals X initial plus V initial T plus 1/2 AT squared. So I can use this for A, and I have an equation for X final of A. I can use it for B. I have an equation for X final B. So this is going to be a big equation. So X final A would be X initial A plus V initial A times time of A plus 1/2 acceleration of A time of A squared. So this right here is X final A. I'm going to set it equal to X final B, which will be X initial B plus V initial B TB plus 1/2 acceleration B time B squared. That is X final for B. And we know that they end at the same position, so these two are equal. Looks big, but let's cross out anything that's 0, because that usually makes things better. So what is 0 in my chart? So let's go. Well, V initial of A is 0. Okay, so this whole term drops out. What else is 0? I've got x initial of b is 0. Okay, so that drops out. Well, okay, that's it. So what does this simplify down to? And I'm also going to note that TA and TB are the same, so I can just not worry about the subscripts there. X initial a plus 1/2 the acceleration of a t squared equals v initial b times t plus 1/2 the acceleration of b time squared. Still looks pretty ugly, but let's throw the numbers in, see what we get. X initial of a, 24, plus 1/2 of a negative 9.8 t squared equals v initial b, 21.7 t plus 1/2 negative 9.8 t squared. I see a t squared term, a t, and a non-t term. This could be a quadratic. Many of the two object problems are quadratics, but if you look at these two terms right here, they're identical. They have the same acceleration and they have the same time. So these two terms, they just cancel each other out. I don't have to worry about them. So this simplifies down to something that everybody can handle pretty darn easily. You can do that, right? So time is 24 divided by 21.7, which gets me, what do I get, 1.1? 1.1 seconds. Okay, is that reasonable? So 1 second for, okay, 24 meters, that's, 25 to 30 feet. You're dropping this one, you're throwing the one up, a second, okay. If it was 30 seconds, I'd know it was wrong. If it was a tenth of a second, I'd know it was wrong. This seems reasonable. Okay, are we done? No, we haven't answered the question yet. We want to know what x final is. So what is x final? Well, for A, here's my equation. For B, here's my equation. Which one do I use? It doesn't matter because they both should get you the same answer because they both end up at the same place. So we said x final A equals x final B. So this is one of the nice things about two object problems is they come with a built-in check. So you can do both, and if you come up with the same answer, you probably did it right. If you come up with different answers, you know you did it wrong. So let's figure out what x final A is. It's going to be x initial A, 24, plus v initial, okay, that's 0, plus 1/2 negative 9.8 times time squared. So if we do the math on that, we get what? What do we get? We get 6, hopefully? No, 18 meters. 6 from the top. So it's fallen 6 meters. Started at 24, that's a negative number, so yeah, it dropped 6. So x final B is, we start at the 0 position, v initial 21.7 times the time, which is 1.1. Oh, I'm running out of room. Plus 1/2 negative 9.8 times 1.1 squared. X final B, we should get the same thing, 18 meters. They end at the same place, 18 meters above ground level, and it took 1.1 seconds for them to reach that place. So don't forget in your problem solving to stop at the end and say, is it a reasonable answer? We know it's got to be between 0 and 24. So if you got an answer of 30 meters, that should tell you you did something wrong. If you get these two different, that tells you you did something wrong. So don't forget to do this very last step of problem solving, which is check your answer for reasonableness, for units. Did you actually answer the question? The question is, how far below the top of the cliff do the stones meet? Oops, we haven't answered it yet. So the question is really asking for 6 meters below the top. So that's the real answer to the question. 6 meters below the top of the cliff. Which means in 1 second, this one dropped 6 meters, and the one that was thrown upwards, well, it was thrown pretty fast. That's like 50 miles an hour. So yeah, in 1 second, it could totally have gone up 18. So now we've got it. We've answered the question. It's all reasonable. There we go. We did it. Good job.